we have this problem here. It talks about an equation of a line, and also talks about an equation of a plane. Now, I'm drawing these very nice drawings for the sake of visualization. I know they're very nice because I do them. And we have some data, obviously. We have this and that. And we have this as the equation of the plane. Well, perhaps it is better to start by talking about the equation of the plane. I think it is more understandable. So this is an equation in 3 coordinates, x, y, and z. It encompasses all points in the 3-dimensional plane whose coordinates give 17 when plugged into this equation. But is there a way we could effectively describe the plane? Is there a more effective way? Or is there any data we can extract from this? And the answer is yes. Obviously, because I'm suggesting this, and this is a tutorial video. So, surprise. And it turns out that if you're in 3-dimensional space, and you have a plane which is 2-dimensional, it is determined by the vector which it is perpendicular to. I want you to imagine this very simply, just on a very simple scale of, just a straight flat sheet, straight flat sheet. So this plane is characterized by the perpendicular vector, which is this one. If I do like this, I get another perpendicular vector. And with any plane that I make, there's always a perpendicular vector. But what determines its height? It's this constant right here. Because if you think about this for a moment, if we are here, and this vector is perpendicular to this plane, then okay, I'm describing a plane. But at the same time, I could be describing any one of these planes, because all of them are perpendicular to the same perpendicular vector. So the equation of the plane is determined by two things. First thing is the perpendicular vector, which we usually call d. And let me tell you this. It's equal to -2, 2, and 1. You can read it off from here, basically. And this will become clear in a moment. And number 2, the height, you could say, I don't want to write h, but the height is this very specific point. So what is this actually? Let's take a moment to really take a look at it and see what it's saying. I want to draw your attention to the fact that for this very specific equation, I can write it, at least the left-hand side, as a dot product of two vectors, x, y, z, and -2 to z, 1. This turns out to be our vector d. And we would like to have these vectors, which we multiply the normal vector by to get a height of 17. This is really how it works. And that's really, a useful piece of information. So I think this is good. I think this is a good introduction. I'll leave this here for a moment. Now let's go to the other equation of the line. So this description of the line involves two things. It involves the vector point A, which, guess what, gets scaled by some constant. So you can imagine there is some movement that's going on. And there is some, well, just some vector, some constant vector. And as a matter of fact, it is usually the case that this is your starting, I don't want to say point, it is a vector, yes, 100%, but in a vector space, it is more space-saving to think of vectors as points. So if I say, you know, this point, I'm really talking about the vector b, which goes from the origin all the way to this point. So this is the vector b. And as you might imagine, vector a points in some direction. Let's say the vector a points in this direction, or in this direction, that direction. Let's say it points in this direction. This is the vector a. And well, for the lambda is just scalings of this a. So you could be scaling the a by 2. You could be, you know, scaling it in the negative direction, you know, by any source of scaling. But fundamentally, this is the idea. So if you take 2 points like this, well, 2 vectors like this, and you would like to scale one of them in such a way, then you get something that describes a line. So I hope this was a good description of these 2 objects which we're dealing with. I know that I am dealing with these 2 objects in a somewhat expository nature, because I do not wish to deal with them in an abstract algorithmic sense. So that's really why I'm doing what I'm doing. I do this. I just put this in a nice box, and then I think we can. I don't want to say finally, but we can start with the problem. So the problem pertains to finding the point at which the line intersects the plane. So let's say it's this point, and we would like to find what this point is. And well, in fact, if this line were to intersect this plane, then it would do so at a specific scaling of a, and that is the way that we are actually going to approach the problem. So let me expand, you know, this equation of the line. You know, it's lambda a plus b. I'm going to write down a. A is the vector 1, -1, 4. I know it's written horizontally here, but it's because we're transposing it. This is usually a more compact way of writing vectors vertically. Anyway, and there's the constant vector b, 4, 5, and 6. I'll expand these terms and group them very quickly, so I get 4 plus lambda, 5 minus lambda, 6 plus 4 lambda. That's not too bad. And then what's next? I would like to now deal with the equation of the plane. Okay, so if I give you a lambda, I get a point or a vector. So this is how it works really. I put a lambda, I get a vector. So we want to know for which lambda, or more precisely for which vector, do we do this, and we get 17. So effectively what I'm going to do now is I'm going to plug in these terms in. So this is what's called the parametric representation of each coordinate. So each coordinate depends on a parameter, which is lambda in this case. So I will plug this in now. Let's see what I get. So -2, 4 plus lambda, plus 2, 5 minus lambda, plus well, z is just z, so I just write 6 plus 4 lambda. This should be equal to 17. So for the vector with scaling lambda that intersects the plane, it should satisfy this equation. I hope you agree with me on that, because if you don't, that would really suck. So we are here, and now we expand. I don't think this is too difficult in particular for you. So you get minus 8 minus 2 lambda plus 10 minus another 2 lambda plus 6 plus 4 lambda is equal to 17, as you can see above. So this is this. And I want you to notice immediately that you have minus 2 lambda, and 4 lambda. So in the end, you just get 0 lambda. 10 plus 6 is 16, and you just take away 18, 8, and then you get another 8. So 8 is equal to 17. 8 is equal to 17 is your result. And probably you're doing the assignment or you're doing the exam, and okay, maybe I should use red for this. You're in the exam or you're doing the assignment and you see 8 is equal to 17, and you're like, okay, this is horrible. Like, what did I do wrong? Well, you didn't do anything fundamentally wrong in the sense that something that would not lead you to the solution. But if you reach a contradiction, this is a sign for a contradiction, then it means that your assumption was incorrect, or was flawed. And what was the assumption? The assumption was that there is a lambda which I can scale a by and add b to it to get a point, slash vector, and this vector would intersect the plane. And it turns out that this will never happen because we reach a contradiction. And if there is no such lambda, then no matter how much I stretch this, or up or down or anywhere, it will never intersect. I want you to think of something like a plane that's like this, and a vector that's, let's say, parallel to it. So these two will never intersect. This is the plane, and this is the vector. These two will never intersect, no matter how you scale it. So it does turn out that they do not intersect at all. That should be the logical conclusion for this problem.